let's talk about properties of logarithms from Algebra 2B, specifically lessons 9 and 10. The focus of this video is going to be use some of the fundamental properties of logarithms to simplify expressions. So for those of you who have never seen a logarithm before, hopefully this will give you a good kind of basic understanding of what a logarithm is and some of the properties we can use to manipulate logarithms and simplify expressions. So what is a logarithm? A logarithm is simply an exponent. A logarithm is an exponent. A logarithm is an exponent. And I'm repeating that because honestly, if there's nothing else that you remember from this video, I want you to remember that a logarithm is an exponent. And it's an exponent to which a specific base is raised to obtain a given value. Don't worry so much about the rest of that sentence because you're going to see what it means when we start looking at logarithmic expressions, all right? A logarithm is just a fancy way to write an exponent, and there are certain reasons why we might want that exponent represented, but we'll get into that later. So if I look at this expression, log base 2 of x equals 6, when I say a logarithm is an exponent, what I'm saying is this expression is equal to 6, and 6 is an exponent, okay? So we've taken an exponent and we've just chosen to describe it in another way. So complementary to exponential form is logarithmic form, okay? So these are just two different ways of representing the same information. Notice that in exponential and logarithmic form, you've got a, b, and x represented there. Now I know you're already familiar with exponential form a little bit. You've seen exponents. In general, you have seen them of the kind where there was a number as the exponent, so maybe 2 to the 5th or x squared, right? Terms like that you're very familiar with. It might be new for you to see x as the exponent, but that is exponential form, and it's its own type of function family. So b is my base, x is my exponent, a is that given value. Okay, a is that given value that was referred to in the definition. So a logarithm is an exponent to which a specific base is raised to obtain a given value. Okay, and this a term doesn't have a proper name. I often call it the result. So if you hear me talking about the result, that's the term that I'm referring to. So it's important to be able to switch back and forth between exponential and logarithmic form because at certain times and in certain contexts, one form will be more helpful than the other. For example, if we were dealing with addition and subtraction, I could write a plus b equals c. But if the situation called for it, I could rewrite that as b equals c minus a. As you guys know, certain situations might demand, things be written in a certain way. In one of these cases, I showed an addition relationship. In the other, I showed a subtraction relationship. But both of the statements keep the values of each of my pieces, each of my terms, the same. Okay? And the relationships are intact. And that's the same sort of thing going on with exponential form and logarithmic form. So, just to continue, if I'm looking at my base, you can see in my example log base 2. That is the b base in the logarithm. That's the b base in exponential form. Next, if we look at the exponent, remember logarithms are just exponents, so 6 is an exponent. In exponential form, that would be represented by that x. And in logarithmic form, again, x. X, a little confusing because of the way these examples are written, but this log base of this number, right, you can see how it corresponds to a. So if I rewrite, this was my original expression, right, log base 2 of x equals 6. And that doesn't really mean anything to us, right? It's not a clear what this expression is trying to ask, what it's trying to ask us to do. By simply rearranging it into exponential form, we get this, 2 to the x equals 6. So 2 to the x equals 6 is the same statement as log base 2 of x equals 6, okay? These have the same information encoded in them. But as you can see, it's simpler to solve this. We can easily take out a calculator or just write it out and figure out what 2 to the 6th is. That's what, 5, there we go. Okay, so again, you'll want to practice just going back and forth between exponential and logarithmic form. the product property of logarithms. So this property tells us that if we want to add logarithms with the same base, we multiply the numbers, or as I was calling them, the results. So if I had two logarithms that I wanted to add together, again, very crucial that they have the same base, I could combine them by multiplying those result numbers together. And let's look at an example. So if I had the expression log base 4 of 2 plus log base 4 of 32, the first thing I do is check and see if they have the same base, which they do. So if I want to add them together, I can rewrite this as log base 4 of, and then multiply those two numbers together. So log base 4 of 2 times 32 gives me log base 4 of 64. Now at this point, I can rewrite that expression. So remember, 4 corresponds to my base. So if I had log base b of, how do I want to write this, of a equals x, if this is my format, 4 is my base, so that became my base over here, right? This expression didn't have an equal sign, but I could just say equals x, okay? I could just say equals x. And x would be my exponent if I rewrote this, right? Because a logarithm is just an exponent. So b to the x equals 64, my result, okay? And again, I assigned this just equal to x because it didn't tell me it was equal to anything else. So I know it must be equal to some variable called x, right? So again, rewriting, I've been able to kind of switch from logarithmic to exponential form. So log base 4 of 64 is the same thing as 4 to the x equals 64. Now that's something we can figure out, right? X must be 3. We know that because 4 times 4 is 16 times another 4 is 64. So 4 raised to the 1, 2, 3, the third power is 64. Okay, so again, notice that logarithms are just another way of talking about exponential equations. Let's look at another example. What if we had log 100 plus log 1000? So the first step is to check and see if we have the same base, but wait a minute, the base is not written here. So what does that mean? Well, it is common for us to assume, if no form is written for logarithms, okay, for logarithms, if they don't give you a base, you can just assume the base is 10, and that's just because it's the common base, okay? It's just an assumption we're allowed to make. So if no base is listed, assume we're in base 10. Since no base was listed for either of these, we're allowed to assume that they are both base 10, which means that we can apply that product property of logarithms. So log base 10 of 100 plus log base 10 of 1000, I can combine them by multiplying those results together. And I get log base 10, or just log of 100,000. So how did I get from here an expression that says log of 100,000 to here? Well, this is logarithmic form. This is exponential form. It's been rearranged. So remember, if no base is written, that means we can assume it's log base 10. So to rewrite this, I always write the base first because I think it's easy to identify. So 10 to the some exponent, well, they didn't list the equal sign. So again, if it's just a logarithmic expression with no equal sign, you can just say it's equal to x. Okay, and I'm allowed to do that because I could do that for anything, right? I could have some number, I could have that number, and I could say, oh, well, that's equal to a, right? I can assign a variable to it, and that's what I'm doing here. So that is my exponent, right? 10 to the x equals this result, which is 100,000. So 10 to the what power equals 100,000, 10 to the 5th power. And again, you could double check that by taking 10 times 10 times 10 times 10 times 10. All right, one more note. Notice that just like I can combine these together by multiplying the result, I can break them down the same way. So let me show you what I mean. If I had like log base 10 of, what's a nice number, 6, If I wanted to, if I had a reason to, I could also realize that, hey, wait a minute, 6 is just 2 times 3. So I could rewrite the expression log base 10 of 6 as log base 10 of 2 plus log base 10 of 3. Okay, so hopefully you can see that those are equivalent expressions because 2 times 3 is 6 and we have the same bases. All right, let's move forward. Once again, we're just going to try simplifying this and expressing it as a single logarithm. So first, note that they have the same base. If this base was anything other than 5, we would not be able to do this. So what are we going to do? We are going to apply the product property of logarithms. And we're going to take those results and multiply them together. So 625 times 25 gives us 15,625. Now I can rewrite this, which wasn't shown here. I can rewrite this, right? Remember, a logarithm is just an exponent, and I can just choose to represent that exponent as x. So if I want to rewrite this, I can take my base, 5, raise it to my exponent, x, and it is equal to this result, 15,625. So 5 to the what equals 15,625? 5 to the 6 equals 15,625. Okay. Now, if you need to see anything again, if you want to see me doing those conversions from logarithmic to exponential form, remember you can always rewind the video, watch it again, give yourself a chance to take good notes on this, and make sure you really understand the examples as I go through them before you move on to a new topic in the video. So just like we have that rule for the product property, we also have the quotient property. So if I have a logarithm with some base of m over n, I can also represent it as log base m minus log base n. So what does that mean? If I have logarithms with the same base and I'm subtracting them, I can divide. When they say divide the numbers, again, this word is just being used because this part of the logarithm doesn't have a proper name. It's kind of sloppy if you ask me. So again, that's what I keep calling the result. Divide the result. So if I had log base 2 of 32 minus log base 2 of 4, first I would note that they have the same base, and that lets me know that I can combine them like this. I can write log base 2 of 32 divided by 4. Okay, log base 2 of 32 divided by 4. What's 32 divided by 4? It's 8. Log base 2 of 8, I'll rewrite in exponential form. So 2 is my base, x is my exponent, 8 is my result. 2 to the what equals 8? 3, right? 2 to the third power. Now there is a reason, you might be wondering, well, how are these even equivalent? I'm not going to go into that explanation here. There is a reason. It has to do with exponents. When you look at exponent properties, it might start to make more sense. If you really want to know more about why this property works the way it does, let me know. All right, let's look at another example. So once again, we're trying to just take this expression and simplify. So I can combine those two expressions because I can see that I've got two logarithms with the same base. So I take the results and divide them. Notice that I'm dividing them in the order they appear. So since it's 48, log base 2 of 48 minus log base 2 of 12, 48 becomes my numerator, 12 becomes my denominator. So just like you see here, log base m minus log base n, m became the numerator, n became the denominator. So 48 divided by 12 is 4. Log base 2 of 4. Let's just slow down that step one more time. So to convert log base 2, 2 is my base. The exponent goes here, and that all becomes equal to this number, my result. 2 to the what equals 4. That's 2 squared, right? So 2 squared equals 4. So again, notice that as we're solving for x, the number that we're solving is just that exponent, okay? All right. Once again, let's just keep practicing. So we have log base 3 of 486 minus log base 3 of 18. I can combine them via subtraction and the quotient property because these logarithms have the same base. So I take 486 and I divide it by 18, once again dividing in order. And if that means you end up with some fraction, that's okay. You have to keep them in the order they appear. So 486 divided by 18 is 27, so this simplifies to log base 3 of 27. All right, once again, let's practice converting that into exponential form. So 3 is my base. Remember, a logarithm is just equal to an exponent, so 3 to the x equals 27, my result. So 3 to the x equals 27. What I have to raise 3 to get 27 is 3 to the third power. All right, so now that you've seen these examples, you can probably see that a logarithm is just something that says, if I have this base and I raise it to some value, I get 27, okay? If I have some base and I raise it to this value, I get 27, okay? Just like right here. If I have this base and I raise it to this value, I get 27. So I could rephrase that as a question, and I could say, to what power do I need to raise my base in order to get this number? To what power do I need to raise my base in order to get this number? Okay. We're going to go through briefly logarithmic inverses. So the natural logarithm, you often just hear it pronounced like ln, but it is the natural logarithm. And it is the inverse function of e to the x. So e is a number that is discussed in your course player. It's just a irrational number just like any other. So for example, you guys are used to seeing pi, and you know that it's a number, this symbol means a certain number. You know, oh, pi is 3.141529, whatever, right? E is the same thing. So e is not a variable, it is a constant number, okay? Read about e in the lesson. So the natural logarithm is the inverse function of e to the x. The natural logarithm is the inverse function of e to the x. And in fact, if we have ln, what it means is a logarithm with base e, okay? So because these are so special, and we won't get into why, because this type of logarithm is so special, a logarithm with a base e is just written for shorthand as ln, the natural logarithm, okay? This function, ln of x, is the inverse function of e to the x, or in other words, it undoes it. Okay, so when things are inverses of each other, they undo each other. Not necessarily, we often think of it as them canceling out. That's not really the case. It's more like they neutralize each other. Okay, so again, ln of x is the inverse function of e to the x. It undoes. These two undo each other. From that, and I would write this down, what we're saying when we say this sentence, what we're really saying is that x equals e to the y has the same meaning as y equals ln of x. X equals e to the y has the same meaning as y equals ln of x. So, why do inverses matter? Well, knowing inverse properties allows us to simplify equations, like you're going to see here. So I was able to, and in fact, let's go back a slide because I think we missed one little piece, which was, let's erase this. Log base b of x is the inverse function of b to the x. Sorry about that. Log base b of x is the inverse function of b to the x. So in other words, we're saying log base b of x undoes b to the x, and b to the x undoes log base b of x. So here's why that matters. If I have something that looks like this, and I've got a 3 as my base and then you see I've got a 3 as my result, and it has an exponent. That means I can simplify this, okay? These two things undo each other. Having the log base 3 and then 3 as my result allows me to simplify this to 2x plus 1, okay? Again, log base 3 and then having this 3 raised to the power, this is an example where we've got those two things undoing each other. So I'm allowed to just simplify and write 2x plus 1. So I would say maybe just write down whenever you see something that looks like that. So we could say like log base b of b to the x equals x. All right. So anytime you see this sort of pattern going on, again, the base and the result like that, where I've got this b to the x, you can simplify it to this. Okay. Let's look at another one. So here, so notice that this one was in logarithmic form, right? Log base b of b to the something. And you're able to just simplify it to the exponent. Now we're looking at it from the exponent point of view. So I've got 12 to the, so 12 is my base, and hopefully you can see this. I'm going to rewrite it just to exaggerate. So I've got this number 12, and then the exponent itself is log base 12 of x plus 7. Okay, again, I've got 12 as a base, and then in my exponent, I've got all this. Log base 12 of x plus 7. Just like before, I can simplify because I've got operations that are undoing each other. Because logarithmic and exponential are inverse equations, they undo each other. So this 12 raised to the log base 12, these things are undoing each other, and essentially I'm able to, again, it's not necessarily that I'm canceling them out, but they undo each other, and I'm allowed to rewrite this entire expression simply as x plus 7. So you can probably see where this would come in handy if you see a very hairy looking question or equation, but you notice something like this going on and you could simplify it. You can see how that would make it much easier to solve. I know this one is kind of a confusing topic. Again, I don't want to burn a ton of time on it. More than anything, I just want you to write down this piece and then maybe this piece as well, which I'll write it bigger to exaggerate. B to the log base b of x equals x. So again, noticing when you've got your base and your result as the same number, they undo each other. Now, again, it has to be the base and the result. We're not talking about the exponent. So if the exponent happens to be the same number or the same variable as one of your other terms, that's okay. That isn't going to be a situation where you apply inverse properties, okay? So again, I want you to write this down and write this down and use them as templates to check for when you can simplify. This one is written in logarithmic form. This one is written in exponential form. All right, let's look at another example. So if I've got x raised to the log base x of 4x, I can simplify this. I can see, remember, if I have my base and my, I've got x raised to the log base x of 4x. So I've got these identical values here and here. So hopefully if you wrote down your template, you're automatically able to see that this fits the criteria we talked about, and we're going to simplify it to 4x. Now notice that this x stayed where it was. It didn't go anywhere. So remember, it doesn't affect the exponent. All this means is I can simplify all this and just rewrite it as the exponent. Remember, logarithms are just exponents. All right, let's move forward. So change of base. Change of base is useful at times for computing something. For example, you might have a calculator that will only deal with values in a base E or base 10. You might have a base 5 or a base 7, and you might think, well, how am I supposed to punch this into my calculator? This is one area where change of base might come into play, but let's take a look at what it is. So if I wanted to change the base, remember this is my base, if I wanted to change the base of some logarithmic expression, I can do that and I can rewrite it as a quotient. Log base A, this is my new base, I'm allowed to pick whatever I want, of x divided by log base A of B. So notice that A is just whatever base I wanted it to be, okay? Just like if I had, I don't know, let's say I had the number 14 and I said, actually let's do a simpler one. Let's say I had the number 3 and then I had 3 plus 1/3. I could say, you know what, it's going to be easy for me to deal with this if I have 3 written in thirds. So I'm just going to rewrite that as 9/3 plus 1/3, and now it makes my addition easier. Change of base is sort of the same thing. So just like where here I was able to pick the denominator that was most helpful for the situation, you can pick the base that's going to be most helpful for your situation. So for example, if I wanted to evaluate log base 3 of 27, we could apply change of base formula, okay? Log base 3 of 27. I'm going to rewrite that as log 27 divided by log 3. Now remember, if there's no base written, we're assuming it's base 10. So this is an example where we're making something easier to punch into a calculator, right? So again, log base 3 of 27 can be rewritten as log of 27 divided by log 3, where my base was 10. And then this is just what you get when you punch it into the calculator, 1.43136. And I don't think we need to know this part too much. Again, this is just calculator manipulation. So again, if chances are you might have a calculator that only wants to operate in log base 10, so that would be the advantage of changing these bases to that. So by finding the log base 10 of 27, finding the log base 10 of 3, you can finally simplify this, and it turns out to be 3, okay? Let's continue. The most important part of this, I would say, as far as learning the new skill is this piece right here. I have the utmost confidence that you can, punch into a calculator and simplify from there. So we're just going to look at one more example for change of base, and then we'll conclude. We're going to evaluate log base 4 of 32. So if I wanted to change this base, once again, if I had a reason and I wanted to change it to base 10, I could do it. Now again, remember, you can change this base to anything. It doesn't have to be 10. That's just the one that we normally have a reason to change to. But I could rewrite this. This could be log base 2. This could be log base whatever I wanted, right? So I've got this expression, log base 4 of 32, and I want to change the base, so I apply my change of base property. So log base 4 of 32 becomes log 32. Notice that the result ends up in the numerator, divided by log base, log 4, excuse me. Notice that the base ends up as the result in the numerator. And just to write that out, so now if you were to type in log 32 into your calculator, you'd get this number. If you typed in log base 4, you'd get that. Then you could substitute those values into your quotient, and you would get 2.5. Alright, so we're going to conclude there. Again, this was more of a basic introduction to some of the properties of logarithms and what logarithms are. Stay tuned for the next video. Thanks, guys.